Hello everyone. Today we're gonna cover a subject called multi-phase flows. The subject will be covered in three parts. In the first part, in our first section, we will discuss the generality of multi-phase flows as an introduction to it. In the second part, we will discuss DPM or discrete phase models, which is one of the major modeling methods in multi-phase flows. And in the last part, we will cover free surface flow, which is the second major method of covering simulating multi-phase flows. So multi-phase flow is basically any flow, any fluid system that has more than one fluid inside. So it could be two gases, it could be two liquids, it could be a gas and liquid, and it can be even more than one fluid. So it could be 3, 4, 5, 6, and even more. As you increase the number of fluids, of course you are increasing the complexity and lengths of your simulation. So have in mind that increasing one fluid to the system will significantly change the problem. In this class, for the purpose of this class, we will be covering only two phase flows, meaning we're going to have two different phases in the system. And in my experience, in the majority of cases out there, you're gonna deal with two or maximum three different flows. And have in mind, we are talking about different phases, not different fluids, meaning it could be liquid water and vapor water in the same system. They are both waters, but since one is vapor and the other one is liquid, it's basically considered two-phase flow. The applications in the industry is a lot. You have in industrial processes, you have riser reactors, bubble columns, fluidized beds, scrubbers, dryers, and these are mostly petrochemical applications. And but you also have in many other applications like internal combustion engines, in inkjet printers, in jet engines, in missiles, in many applications. So that's but in here we will not discuss any specific application. We will go around talking about the general concepts of simulating multi-phase flows. So the definitions, as we said, you can have simultaneous flows, meaning materials with different phases or materials with different chemical properties but in the same state or phase. So it could be materials with different phases like gas and liquid or solid, and I forgot to mention in our previous slide, it could also be solid. So you could have liquid and solid, you could have solid and gas, which happens a lot in a phenomenon called solidification, which gas turns into a solid or a solid turns directly to the gas. So it could be that, or it could be same phases, liquid and liquid, but different materials like water and oil, like honey and oil, different materials. The second important definition is the definition of the primary and secondary phase. So in any multi-phase flow, one of the phases and only one of the phases is called primary phase, and the second one or the other phases are called secondary phases. So distinguishing between your primary phase and secondary or other secondary phases are very important because many, as you would see in discrete phase modeling, free surface modeling, and also many other models, the basis of the model is on that what is your primary and what is your secondary. How would you distinguish between them? Basically, the primary phase is the continuous phase, while the other is the dispersed phase inside the continuous phase. So you can consider the fluid with the majority of the volume is considered usually the primary phase. For example, if you're taking shower and you want to simulate that shower, your air, which is everywhere, is considered your primary phase, and droplets of water coming out of the shower are your secondary phase. Or the other example is in internal combustion engines. When you're spraying fuel through injector to the cylinder, your fuel which is being injected is your secondary phase, and the air inside the cylinder is considered to be your primary phase. Based on this definition, we can define something called volume of fraction or volume fraction, which is very useful, especially in our free surface modeling. In volume fraction, basically it refers to the volume fraction of the secondary phase. So how much of the secondary phase you have divided by the whole volume of the cell. So if, and by cell we mean the cells in the mesh in your system. So for example, if your one of the cells is half full with the secondary phase, its volume fraction is 0.5. If 80% of it is full with secondary phase, volume fraction of it is basically 0.8, and so on and so forth. So it goes from 0 to 1, 0 being zero amount of secondary phase in the cell, and of course you can't have vacuum, right? When we say secondary phase is 0, it means the primary phase is 100%. So that's volume fraction of 0, and goes up to 1, which when it is 1, it means the whole cell is full of your secondary phase. There are different multi-phase flow regimes depending on the type of interaction between the secondary phase or phases and the primary phase. They are divided basically to 6 major type of flow. The first one is called bubbly flow. So in bubbly flow, you have discrete gaseous bubbles in a continuous liquid. So wherever you have bubbles, and those are gas bubbles inside a continuous liquid, it is going to be considered as a bubbly flow. The other one is called droplet flow. So droplet flow is very similar to bubbly flow, but in here discrete fluid droplets in a continuous gas. So this is called droplet flow. So for example, going back to the example of the shower, the droplets, water droplets that is pouring down from your shower, it's basically a droplet flow. Why? Because your continuous phase is gas, it is air, and your discrete phase are in the form of bubbles dropping down from your shower. For the bubbly flow, have you seen, you have those glass pots full of water, you put it on the stove, it starts forming bubble on the bottom, and the bubbles are rising up until to the boiling point. That's a form of your bubbly flow. The next one is particle-laden flow. In a particle-laden flow, basically now you have discrete solid particles in a continuous fluid. So it's a discrete solid particles in a continuous fluid. For example, if you get a cup of the seawater from the shorelines, usually you have sand inside, right? those sands inside your cover wire is called basically particle laden flow. So it is solid particles in continuous fluid. And remember, I gave the example of solid particles in liquid, but it's a fluid, right? It can be a gas also. Then you have the slug flow. Slug flow is basically large bubbles in a continuous liquid. So slug flow is very similar to bubbly flow, except in bubbly flow you have relatively small bubbles in your continuous liquid. But in slug flow, what happens is those small bubbles are united together, forming, if you may say, a very large bubble considering your domain, and that's called slug flow. So you could consider slug flow extreme case of the bubbly flow, where the bubbles are so many that they have united, forming a very big bubble. The next one is annular flow. Annular flow continues on the line of bubbly flow and slug flow, which means annular flow is an extreme case of slug flow. If you have too many of these slugs in the liquid, they are going to eventually unite, forming a hollow gas part with liquid in the green on the periphery. This is called annular flow. So it goes bubbly flow, slug flow, and the annular flow. The next one, which is esterified or free surface flow, as we call it. So in a free surface flow, you basically have immiscible fluids separated by a clearly defined interface. So in here, the case is different. In here, the fluids are not mixed. They are immiscible, so they can't mix. In this case, they are defined by a clear interface, like the water you have in a bowl, the most obvious case, or the water in the pool, or many other cases that you can have. So this is called free surface flow. Free surface flows are very important in the industry and in nature, and that's why we have dedicated a full section for free surface flows, how we model them, how we simulate them. So now, similar to what we discussed in turbulence flow, going back to our what we have emphasized over and over again, that if you are solving a direct numerical simulation, meaning you only have those 5 equations, 3 velocities, temperature, energy, and continuity, you do not need to know any of this, that whether there is turbulent or laminar or there is multiphase or not. You will solve the flow with your 5 equations, and whatever the flow is, it will show up in the results. But as we said over and over again, that requires a lot of mesh, and that requires a supercomputer. So for us, we need to use auxiliary physical models. Same in here in multiphase flow, we need to use auxiliary extra equation, and for that reason, you as the user must know prior to your simulation that what is the characteristics of your multiphase flow. What is the flow regime for your multiphase flow? Because only you can model one flow regime at a time. If it is annular flow, you're going to model annular flow. If it is bubbly flow, you will model bubbly flow, so on and so forth. And similar to turbulence flow, remember, predicting and simulating the transition between laminar flow and turbulent flow was extremely difficult. You remember that? It was even more difficult than simulating either turbulent or laminar. Here is also the same. Predicting the transition from one regime to another is possible only if the flow regimes can be predicted by the same model. So meaning, if you can use one single model for two different regimes, you can basically predict, and by predict we mean in your simulation, the transition from one to another. Otherwise, you can't. If the simulation method, if the model you're using for simulating the two regimes are different, you can simulate each regime differently, but predicting the transition is not possible, and you have to do that through theory and experimentation and so on and so forth. So the modeling approaches, there are many modeling approaches which they are increased basically from top to down, and they increase in complexity. So number one is Lagrangian method, and we will explain about this because Lagrangian method is basically the backbone for discrete phase modeling. This is arguably easiest one in terms of development and application of it, but on the other hand, it also could be very difficult if you're dealing with a very large flow, or you're dealing with extra phenomenon like boiling, freezing, phase change, collision, so on and so forth, right? This second one, which is in the middle, is called algebraic slip model. And basically this is a dispersed phase in a continuous phase. So in here it is very similar to Lagrangian modeling, except you solve one equation for the whole thing. We will not consider this in this class, but it's useful specifically when you are solving chemical reactions or chemical mixtures. The last one is two-fluid theory, or it's better to call it multi-phase theory, multi-fluid theory. Basically, it's an Eulerian model, and it solves as many equations as there are for the phases. So in here, which is in terms of development and establishing the solution, is the most difficult one, because if you have two phases, you are solving two set of 5 equations. If you have 3 phases, you are solving 3 set of 5 equations, so on and so forth. And even more difficult than that, because you have to also simulate the interaction, the surface between them. And one more level of difficulty, what if there is also phase change between them? So this is the most difficult one that we will try to cover it in our free surface flow modeling. So just give you an overview before diving into the discrete phase modeling and free surface modeling. So in multi-phase flows, first you have to know what is the flow regime. Is it a bubbly flow, droplet flow, particle-laden flow, slug flow, or what the flow is, because that's the basis to decide what would be your simulation method, what kind of simulation method you will use. So that's the basic. Then you will, based on that, you will choose the simulation model. So you will choose, okay, if I have a droplet flow, is it better for me to use Eulerian, algebraic, Eulerian granular, volume of fluid, or what? If I'm dealing with bubbly, now what model should I use? So the second thing you will decide about it is the model, simulation model that you will have. Once you have these two, you have the basis for your simulation. Now the only thing remaining is to see if there is any other thing extra. If there is evaporation, if there is reaction, if there is suspension, if there is filtration, or any other things. Because Every single extra phenomena will add one or two or more extra auxiliary equations, which makes the job more difficult. Okay, now that we have discussed here everything, we will go and dive into our first simulation model, which is discrete phase modeling.